Hi guys, I am Dr. Ganesh and welcome back to my video series on machine learning. In this video, I am going to introduce you about one of the very popular learning algorithms called Naive Bayes. It's a classification algorithm which works primarily based on the principle of probability Bayes theorem, and it's naturally a type of supervised learning. Imagine two people, Alice and Bob, whose word usage pattern you know. To keep example simple, let's assume that Alice uses combination of three words love, great and wonderful more often, and Bob uses the words dog, ball, wonderful often. Let's assume you received an anonymous email whose sender can be either Alice or Bob. Let's say the content of email is I love beach sand. Additionally, the sunset at beach offers wonderful view. Can you guess who the sender might be? Yes, so you understood it is probably from Alice because of the word combinations. Now let's add a combination and probability in the data we have. Suppose Alice and Bob uses following words with the probabilities as shown below. Alice uses love with probability 0.1, wonderful with probability 0.1, great with the probability 0.8, whereas Bob uses wonderful with probability 0.5, love 0.3 and deal 0.3. Now the sentence is wonderful love. Now what do you think? Who might have said that sentence? By looking at the probabilities, we could say Bob, because Bob uses wonderful with a very high probability and love with a high probability compared to Alice. And this is a very typical situation where we can apply Bayes theorem. Naive Bayes classifier calculates the probabilities for every factor. Here in case of email example, it would be Alice and Bob for given input features. Then it selects the outcome with highest probability. This classifier assumes the features are independent. Hence the word naive. Even with this, it is powerful algorithm used for several examples, several real-world use cases, including real-time prediction, text classification, spam filtering, recommendation system, etc. Let's take an example. I have taken this sample from Geeks for Geeks. Thanks to them for a very nice article on naive-Bayes classifiers. This is a very typical golf playing example used widely in machine learning. There are a few features: outlook, temperature and humidity. Outlook, temperature, humidity and windy. Based on these factors, we would like to see if we should play golf, and we have historical data available on how someone has made a decision. Assumptions. The fundamental naive-Bayes assumption is that each feature makes an independent and equal contribution to the outcome. With relation to our data set, let's understand this concept. We assume that no pair of features are dependent. For example, temperature being hot has nothing to do with humidity, or the outlook being rainy has no effect with winds. Hence, the features are assumed to be independent. Now, equal. Each feature is given the same weight. For example, knowing only temperature and humidity alone can't predict the outcome accurately. So all features are assumed to be contributing equally to the outcome. Let's recollect Bayes theorem. So Bayes theorem is the posterior probability P of C given X is P of X given C, which is the likelihood, and P of C, the prior probability of the class, divided by P of X, the predictor prior probability. So basically we are trying to find the probability of an event, say A, if I take the smaller example, the smaller equation, given that B is true. So probability of A given B, even B also termed as evidence. PA is the priori of A, that is the prior probability of event before evidence is seen. Evidence is an attribute value of an unknown instance. Here this is event B. And P of A given B is a posterior probability, that is probability of event after evidence is seen. According to this example, the example of playing golf, if it is P of Y given X, it will be P of X given Y times P of Y divided by P of X. Now what is Y here? It is the class variable to play or not to play golf. And X are nothing but the features, the windy or outlook or humidity, etc. So X will be given us X1, X2, etc. Here X1, X2 could be rainy, hot, high, false. Given that we would like to predict Y given X. P of Y given X means probability of, so in this example Y is no, so probability of not playing golf. Given that the weather conditions are rainy outlook, temperature is hot, high humidity and no wind. So Naïve's assumption. Now it's time to put the Naïve's assumption to the Bayes theorem, which is independence among the features. So now we split evidence into independent parts. So let's substitute X by expanding and applying chain rule. So P of Y given X1 comma Xn is P of X1 given Y times X2 given Y times etc. as you can see in this equation. Now you can obtain the value for each by looking at the data set and substitute them into the equation. For all entries in the data set, the denominator does not change, it remains static. Therefore, the denominator can be removed and a proportionality can be introduced. In our case, the class variable has only two outcomes, yes or no. There could also be multivariate or multivariable classification. Therefore, we need to find the class Y with maximum probability, so which is highly likely to occur. So argmax of Py, pi of Pxi given Y for all I from 1 to n. So using this function, we can obtain the class given the predictors. Let's take our example a little further. For computing all this, we need to do some pre-computations to our data set. We need to find xi given yj for each xi in x and yi in y. And all these calculations are demonstrated in these tables. I request you to pause the video here, understand the tables, and then move forward. So let me briefly describe one example for Outlook. So there are two cases when Outlook was sunny. There are two cases for which golf is played yes. Three cases for which golf is played. Golf says no. So probability of S is 2 over 9. 9 is a total number of entries here which has yes. And P of no is 3 out of 5 because there are total 5 entries here with no when Outlook is given. So we calculate this for all of them and we do this for everything. And now we come back and then cumulatively take how many total yeses? 9 yes. So 9 out of 14. Total no's are 5. 5 out of 14. And this is a pre-computation. So in the figure, we have calculated Pi given x, Pxi given yj, yi for each I in xi and yj in y manually in the tables. So for example, probability of playing golf when the temperature is cool is 3 out of 9. So you can see here, temperature is cool is 3 out of 9 because 9 total 9 says yes. And we have found the class probabilities for the yes and no at the last table. So now we are done with our pre-computations and the classifier is ready. So let's test this on a new set of features. Let's call it today. So assume today is sunny, hot, normal, and no wind. Very true for at least a place where I live. So probability of playing golf is given by probability of yes given today is P of sunny outlook given yes, hot temperature given yes, normal humidity given yes, no no, wind given yes, and P of S divided by P of today. And probability is to not play similar. Here P of S given today is 0.014, no given today is 0.006. So 0.014 divided by sum of them, and P of 006 divided by sum of them. Now yes given today is greater than no given today, so the prediction will be yes for today. I will play golf. Social distancing, man. We can't play right now. So what are the pros? It's easy and fast to predict class of test data set. It's also perform well in multi-class prediction. When assumption of independent holds, a naive-Bayes classifier performs better compared to other models such as logistic regression, and you need less training data. It performs well in case of categorical input variables compared to normal numerical variables. For numerical variables, normal distribution is assumed, bell curve, which is a strong assumption by the way. So what are some of the cons? If categorical variable has a category which has not observed in the training data set, then the model will assign a zero probability and will be unable to make a prediction for that particular category. This is often known as zero frequency. To solve this, we can use a smoothing technique. One of the simplest smoothing techniques is called Laplace estimation. On the other side, naive Bayes is also known as a bad estimator. So the probability outputs from predict are not taken into account seriously. Another limitation is the assumption of independent predictors. In real life, it's almost impossible that we get a set of predictors which are completely independent, isn't it? Yeah. Typically, a rain and wind may be related to each other. So let's briefly look at how do we solve zero frequency problem. An approach to overcome zero frequency problem is to add 1 to the count for every attribute value class combination when the attribute value does not occur in the class value. Let's take an example. Assume time zone US, the spam size yes and spam size no has some values, whereas when time zone is EU, there are no values. So the P of time zone equal to EU will become 0. So to solve zero frequency problem, we will add 1 to each of them to get us some probability. This will help us estimate and understand the effects. Thank you guys. Hope you like my videos. So please feel free to subscribe, comment, share your feedback, share with your colleagues. Thank you very much. Bye.